So I've just shared my screen. You should be seeing a piece of paper on my desk that says Quiz 9. And we're working with 1R, 3R, 1-bromo, 3-methyl cyclopentane. So it's a ring, 5-membered ring. The first battle is to make sure we draw 1R, 3R, 1-bromo, 3-methyl cyclopentane correctly. So what I did was I drew the 5-membered ring, and then I just put the bromine and the solid wedge out of the page and the hydrogen in the back. And then on the 3 position, I put the methyl group up and the hydrogen on the back. I don't know if that's the right one yet, but it's easiest to determine whether something is R or S when the hydrogen is pointing back. So I chose to put them straight back to begin with. So with the hydrogen pointing back, bromine is the top priority substituent. This CH2 is attached to a carbon that has a methyl group on it. This CH2 isn't, right? There's just another CH2 there. So this side of the ring takes priority. Bromine going to this side of the ring, going to that. That is an R stereocenter. So that's the correct stereocenter at carbon 1. At carbon 2, this CH2 outranks this CH2 because the next carbon has the bromine on it, so that's number 1. This part of the ring is number 2, the methyl is number 3, the hydrogen is number 4. So that's actually an S stereocenter as written, which means I need to switch that one. So the cis isomer is 1R3S, and the trans isomer is the one I want, the 1R3R. So this is the substrate we're working with. Trans 1-bromo 3-methyl cyclopentane, and I've drawn it so that the bromine is up and the methyl is back. Right? So we're reacting this under 2 sets of conditions, one with sodium fluoride and DMSO, and one just heating in methanol. So in the case with sodium fluoride and DMSO, you're told that that's an SN2 reaction. So case 1, we know it's an SN2 reaction, which means that we know immediately that the rate law can be written as minus D substrate. If you want, you could have written out that name. dt is equal to K times the substrate concentration times the concentration of fluoride ion, right? Because it depends on both the substrate and the fluoride. That's second order overall kinetics. We know that it goes with inversion of stereochemistry because it's stereospecific. And we know that what stereospecific means is a single pure stereoisomer of reactant becomes a single pure stereoisomer of product. Right? So with inversion of stereochemistry, the bromide is going to leave from the top face and the fluoride is going to come from the back face. So the product will be unchanged here at carbon 3, since carbon 3 is not reactive, but it will have flipped. So this will be the 1s3r stereoisomer, right? And just a single product, right? So it's a stereospecific reaction. And if we wanted to, we could write that out as 1s3r, 1-fluoro, 3-methyl cyclopentane. Hold on, I need to respond to a question here. Okay, so this is the product, right? Here's the rate law, that was one of the parts. Here's the stereochemical consequence, inversion of stereochemistry, that's another product. Here's the, or another section, right? So A, rate law, B, stereochemical consequence, C, I've drawn the product. Now I want to show the mechanism. Feel free to break in by talking, since I'm not actually looking at my screen. If you type something, I might not see it, but if you speak, I will hear it. So what I want to do is I want to draw this molecule, this one, sorry, the correct one, in such a way that the bromine is in the plane of the page. So the best way to do that would be to show the 5-membered ring. Right, so we've got a solid wedge and a dash wedge. We've got our hydrogen here and our bromine sticking out. And if I turn it kind of to the right, the bromine would be pointing out to the right. This methyl group then would be pointing off the left on carbon 3. That would be this carbon. So the bromine is, or the methyl group rather, is out here, and the hydrogen is over there. Right? So that's a reasonable drawing. Fluoride is the nucleophile. So the negative charge on fluoride, and the fluoride is going to come in from the back side, the opposite side of the bromine. This is a concerted reaction. The fluoride lone pair is going to attack this carbon at the same time as the carbon-bromine bond is being broken. And because it's a concerted reaction, I want to draw the transition state so that I will have a fluoride with a partial negative and a partial bond to the carbon, and then also a partial bond to the bromide, which is leaving, and it will have a partial negative sign on it. And then my hydrogen will be pointing straight up. There's my carbon, and I will have my ring looking like this with the methyl group sticking out on the right and the hydrogen on the left. So there's the transition state, straight line between the fluoride nucleophile and the bromide leaving group, right? Because it's 180 degrees, basically a trigonal bipyramidal geometry around this carbon, right? And that will end up putting the fluoride on the same side as the methyl group, which is what we see in our product. And then I can draw the product if I want to in that same perspective drawing, where now the hydrogen is where the bromine used to be, and the methyl group is over here, hydrogen is over there. Right. So there's the mechanism. And then the last thing I want to do is draw the energy diagram for this. I'll stick that above here. We've got the energy, we've got the reaction coordinate, which in this case is percent completion of reaction. Right, starting materials here, products down there. Because the carbon-fluorine bond is stronger than the carbon-bromine bond, it'll be an exothermic reaction. Single elementary step, concerted reaction with just one transition state. So that's what the energy diagram looks like. So now we want to take that same material. See if I can get these to show up at the same time. So we're taking the same material and we're looking at the reaction with just heating and methanol, which is the SN1 reaction. So we know this is going to be stepwise. It's a solvolysis, so there'll be 3 steps. So we're going to start with our material. This time we're not going to show transition states. That's unnecessary for the SN1 reaction, because the first step is quite endothermic, which makes it a late transition state. It looks like the carbocation intermediate. So the bromide is going to leave, which is going to generate a planar carbocation. And now because that's a planar carbocation, the nucleophile, which in this case is just the solvent, right? That's the definition of the solvolysis reaction, where the solvent is the nucleophile. That's going to attack, and it can do it from either the top or the bottom. I'm not going to show it both ways. SN1 reaction is equilibrium, unlike the SN2 reaction, which is generally not. So the carbocation could just add bromine again to go back. So I'll show the product having come from the top face, which means I'll put the hydrogen back. But you could equally well have shown it coming from the bottom. This stereocenter is unchanged. And then in the final step, there's just a rapid proton transfer where the methanol pulls that hydrogen off, and we're just switching the hydrogen from one oxygen to the other oxygen. That's actually also in equilibrium. This whole thing is an equilibrium reaction. So it's a more involved mechanism because it's happening in 3 steps instead of a single step. And the product is an ether. And then we also generate some acid, which I won't show. So that's one of the possible products. But since it's racemic at C1, right, it's not a racemic mixture because it's a mixture of diastereomers, we get a mixture of diastereomers cis and trans. So the other product has the hydrogen up and the OCH3 back. Right, so we have the cis isomer here, we have the trans isomer there. And we probably get those in very close to a 1-to-1 mixture because this additional stereocenter here is not close enough that it's likely to have a large effect. Right. So that was part D if I'm going by the previous one, right? That's the mechanism. The energy diagram for this one is also more complicated. So we've got an initial endothermic step that goes up to that carbocation intermediate, and we've got an exothermic step that takes us down to the protonated alkyloxonium ion, and then the third step, this is just proton transfer. Proton transfer steps have very small activation energy, so that's a very rapid step towards the end. And you'll notice that both transition states look like the carbocation. So that was part E, the energy diagram. And it doesn't matter what order you do these in. So then if we want to do part A, which is the rate law, right, this is unimolecular rate determining step, which means it'll have first order observed kinetics. So the rate, which I write as the disappearance of substrate with respect to time, is equal to K times the substrate concentration. The stereochemical consequence is proceeds with racemization at the reactive center, which in this case is carbon 1. No change in stereochemistry at carbon 3 because that's not where the reaction's occurring. And I've already drawn the products, right? So part C, here are the 2 products, the cis and the trans isomers. Are there questions about the quiz?